Hi everybody, my name is Rinki Jairam. I am here to present on the topic of NIOS II architecture, which is a part of my advanced computer architecture project for summer 2015 in my university. NIOS II is a 32-bit embedded soft processor that can be instantiated on an Altera FPGA device. A soft-core processor is a microprocessor fully described in software, usually in a hardware description language, which can be synthesized in a programmable hardware such as FPGAs. NIOS 2 incorporates many enhancements over the original NIOS architecture, making it more suitable for a wider range of embedded computing applications. A complete instruction set, including operand addressing methods, is often referred to as the instruction set architecture of a processor. The functional units of the NIOS 2 architecture form the foundations for the NIOS 2. NIOS 2 has three instruction types: I-type, which is used for the load and store instructions, R-type, which is used for the arithmetic instructions, and J-type, which is used for the jump instructions. Traditional MIPS Datapath. The MIPS instruction set architecture is a RISC-based microprocessor architecture that was developed by MIPS Computer Systems Incorporation in the early 1980s. MIPS RISC microprocessor architecture characteristics include fixed-length, straightforward decoded instruction format, memory accesses limited to load and store instructions, hardwired control unit, a large general-purpose register file, and all operations are done within the registers of the microprocessor. Every instruction in RISC architecture can be implemented using 5 clock cycles. The 5 stages are the union of all the operations required by all the instructions. That is, they are the instruction fetch, instruction decode, execute, memory access, and write back. This slide shows the data path of the implemented design. The data path is divided into 5 stages. The very first stage includes PC block, which is a program counter that points at a location in the instruction memory that holds the instruction. And the incrementer performs the task of incrementing the current address by a value of 4. The second stage is the instruction decode stage, which consists of various modules. The first module is the instruction divide, which breaks the instruction field into various subfields such as opcode, OPX, source register, target register, destination register, and immediate, and produces them as an output. The opcode and OPX are given as input to main control module, which generates various control signals for all the stages. The source register and target register are used to point at the locations in the register file. The 16-bit immediate offset is given to assign extender block, which generates 3 different 32-bit versions of immediate offset. The third stage is the execute stage. This stage generates the branch address, data memory address, results, and write back register address. The read data 1 from previous stage is fed to ALU. ALU either generates an address of data memory or a normal result. The ALU gives out branch result when the comparison is done for branch operation. It performs the operations such as addition, subtraction, multiplication, comparison, and logical OR operation. The fourth stage is the data memory stage. The read and write operation related to memory are controlled by the read mem and mem write mem signals. The address from where data is to be read is given by the ALU, whereas the data to be written is provided by the previous stage read data 2. The last stage is the write back stage. This stage is the smallest one, which gives the address of the register where data is to be written in case of an R-type operation. Another important block is the hazard detection module. This module basically is used to detect read after write data dependency and give 2 control signals, which are stall and instruction flush. The data dependency occurs when the read and write operation is done on same register. In such a scenario, this module pauses all the pipelines and allows the write back stage to complete its operation. This is the benchmark program, that is a dot product of 2 vectors. R2 points to A vector and register R3 points to B vector, and the result or the product is placed in register R5 and stored in memory. The left part of the table represents the pseudo instructions which has to be changed to native RISC instruction. But this sequence of code has data dependency and hence had to be improvised. The code is improvised by restructuring it or by reordering it so as to avoid data dependency. This slide depicts how the codes are initialized with respect to their memory. The screenshot shows that the instruction for RI is fetched. It is decoded, giving out register R2 as a target register and immediate value as hexadecimal value of 4, which is the location of the first element of vector A. In execute stage, the ALU generates the memory location address, that is 32-bit hexadecimal value 4. In memory location, these values are carried forward. The pointer for vector A and B is loaded in the respective registers as per the test program. The register R4 is first cleared and then loaded with the count n, that is 6, as per our program. It can be seen that there is a read after write dependency between clearing R4 and loading 6 in it, so there is a stall. This slide gives the location and data for vector A and B. The loop count is loaded from memory location 0, that is memory location 0 has the value of 6. Both the memories are byte addressable. Every incoming address is right shifted by 2 and the respective location is addressed. As per the program and the test data, the first element of vector A is loaded in register R6. The first element from vector B is loaded in register R7. The loaded data is multiplied and stored in register R8. The writing operation is actually as read-write WB signal is high. In this screenshot, the previously obtained product is added with contents of register R5 and stored back in it. The pointers in register R2 and R3 are incremented and the loop count in register R4 is decremented by 1. The first branch occurs and the pointer jumps to a new location of the instruction memory and the instruction from the previous location is discarded. Next, elements of vector A and B are loaded in registers R6 and R7 respectively. This loaded data is multiplied and stored in register R8. The contents of register R8 is added with those of register R5 and stored in register R5. The pointer in the registers R2 and R3 are incremented, whereas the loop count in register R4 is decremented by 1. This is the expected result according to the program, which is a value of 133 in decimal. The final product is stored in register R5 in hexadecimal format. The count in R4 decrements by 1, so it becomes 0, indicating the end of the loop. As the loop count is 0, there is no branch and the final result is written in memory location of data memory, which is the next free memory location. This is followed by the execution of branch instruction, that is stop. This slide shows the features of the NIOS II design implemented. The data hazard detection unit is incorporated, which uses stall, thus avoiding the raw hazard, that is a read after write data hazard. The ALU control is incorporated in the main signal, in the main control unit. It has 32 cross 512 instruction locations in the instruction memory, 32 by 32 internal registers and 32 by 1024 data memory locations. The entire operation takes 266 cycles to be completed. Future scope or future enhancements. Stalls in the branching can be reduced further if the branch unit can be moved to the previous stage. Additional cache memory and data forwarding unit can be implemented. ALU can be improvised to include more number of operations. Data and instruction memory can be enlarged for more data storage to make it more efficient. Thank you.